Thanks for tuning back in. We're going to discuss our final part of the zone system. This is the bypass duct. We started introducing that on our last video. We're going to cover how that bypass opens up, what you can expect to see as that cold air returns back to the unit, and why that DATS, discharge air temperature sensor, is important so we don't lose oil in that compressor, freezer coil, and have issues. Blower motor issues too. Involving motors failing due to high static and nothing being done about it. So stay tuned. All right, thanks for tuning back in. Behind me, we're just going to get right into it. There's no labs today. We're just going to discuss zoning with a bypass. There are a lot of zone systems out there that are not designed with bypass ducts. A lot of people think that they're not necessary, and there's a misunderstanding on why it needs to be there in general. I want to try to make that less confusing by giving you this example behind me. I want to first go over the drawing so it's understood. This is an air handler, blower wheel, blower motor, evaporator coil, return air plenum, return trunk line. You can see that the arrows are red because in cool mode we have warm air going to a cold coil. That's why it's outlined in blue. We're exchanging the heat, leaving cooler air, entering a blower, going across the heat strips, which are not running here, hence they're black, and then into the supply air plenum where we have our discharge air temperature sensor wired back to our zone board, here the DATS. And then going up, we have a bypass damper, the bypass trunk line or the bypass duct coming right back to the return. If you notice, I don't have any arrows here because this damper is in the closed position. Past that, we have our supply trunk line. That air continues to move through that main distribution box that has the supply air dampers on it. I've got some different size supply air dampers, so this would be a 3-zone application where the bypass is right on the supply plenum going back to the return plenum. So a lot of confusion on people thinking that this does not have to be there, that you can zone out a home without it and it'll be flawless and there won't be issues. And I'm here to tell you that that's not the case. This unit was designed to run on a certain static pressure. When we start to close these dampers off, then we're going to increase that static pressure because we're cutting some of the supply ducts that are sized to come off of that unit to allow that static pressure to maintain within that range. Right? When we start closing that down and we start reducing those trunk lines, then that static pressure is going to increase. That's going to stress that blower motor and it's going to cause some failures there. Plus, not to mention, we're going to start flooding out our evaporator coil with liquid refrigerant. We're not going to get enough heat exchange through the coil because we can only push as much air as we're pulling in. And if I have no problems with my return side, but yet I'm causing problems on my supply by closing dampers down and not allowing that air to go back anywhere, then we're going to slow the amount of CFMs on that coil down. So for example, if each one of these was putting out, say, let's just say for example, 1,000 CFMs on this one, and this was 350 CFMs, and this was 650 CFMs. In total, I had 2,000 CFMs, and say this was a 2,000 CFM air handler, 5-ton unit. If I were to close off this 1,000 CFM supply air duct, then I only have 1,000 CFMs to distribute air at the proper static pressure. So I'm going to get more velocity out of that the moment that closes down, so it might feel great in those zones, but at the expense of that motor running at a higher static. Not only is it running at a higher static, but now we're not pushing 2,000 CFMs out of that air handler, because you're not going to take the 1,000 CFMs that you lost here and it's not going to just push 500 more CFMs here and 500 more CFMs here. It's not going to happen that way. So we need to have these bypass ducts. So when we close off any one of these zones, that additional air has a way to come back to the unit. Now, when it comes back to the unit, what we're looking for is to come back to the unit to alleviate that static pressure. However, the common problem in our industry is the misunderstanding that once you solve that one problem and you don't have motor issues, you have another issue, and that's cold air coming back to your evaporator coil. The coil will freeze. And so people think these bypass ducts should not be there because, you know, you just can't win. But it's, if the bypass is sized correctly and you install these discharge air temperature sensors, then when the supply air plenum starts to drop, which I'll show you here in a little bit with some figures on the board, as cold air starts to come back around, you're going to drop the supply air plenum even more. That discharge air temperature sensor is going to read what that resistance is, and it's going to tell that board that it's pretty cold and you need to shut that condenser down. We just don't need it. And so it just times out that condenser for, you know, the length of time that that low limit is there. So if that low limit's set at 44 degrees Fahrenheit, then that discharge air temperature sensor is going to have that board telling it to drop out that Y call to that condenser. That condenser will not run during this time frame. That might take the length of time for one of these zones to satisfy, not even using the condenser. That happens quite often. After the plenum comes up to a safe temperature range, then what will happen is the zone board, if it's still getting a call for Y from one of these zones, it will allow that condenser to come back on. So it's just going to constantly toggle the condenser on and off, but it's not going to short cycle it. It's going to allow it to have enough time so it doesn't have a problem with anti-short cycle issues or anything like that that are also a problem in our industry, where things are bypassed, time delays are bypassed, and people do that and they forget that they leave them in those modes. Well, this zone board's not going to allow that to happen. You can manually, bring something on if you're in front of this electrical panel or this zone board, and if you're testing things, so you don't have to wait on those time delays. But the way this is set up, if you wire it the way it's supposed to be wired, it's only 2 wires, put that in a supply air plenum, it's going to run just fine the way it's supposed to. We had a video that we released on sizing bypass ducts. Definitely watch that one, because we're not going to get into that in this video. But I want to show you mechanically how these dampers can close and what will happen with that bypass damper, because you're not able to really see all this like you can here. And so I'm going to do the best I can to kind of help you out a little bit. So right now in this picture, we have warm air from the return coming through the return plenum, going through the evaporator coil. We're exchanging the heat out of that. We're going into the blower. We're not being heated back up through the heat strips. We're going through the supply air plenum. Those blue arrows, they stop right here because this bypass is closed, because there's no static exceeding the limit of what this bypass damper needs to open, because all these were sized properly. And with that supply air moving through that supply trunk line, through that main distribution box with those dampers, and it's just going out to those zones. But if we were to close one of those zones down, let's just say that we close this zone down, I'm going to, actually that zone's already closed. Yep, I believe that zone's already closed. Okay, so if that zone is closed down and these 2 zones are opened up, then what's going to happen is this bypass, it's going to open up as well. And so it may not open up all the way. It may open up just enough to allow some of that air to move around it and fill, yes, cold air into the bypass trunk line. So how that would basically look is we would have cold air, I'm going to get my mark big, coming through here, and it's going to mix in with this warm air. Now, that warm air may be, say, 75 degrees. Well, if you have a plenum that's at, say, 55 degrees, then yeah, now you do have 55-degree air coming in, and it's mixing with that 75-degree air. So you're not technically getting 75-degree return air on that evap coil now if you have 55-degree air coming in to that return plenum. It's going to mix, and it's going to probably give you an average of maybe 60 degrees, right? And so if I have 60 degrees coming in here and I'm exchanging heat off of that, then I'm no longer 55 degrees here, right? I'm probably going to be more like 50 degrees, or I'm probably going to be more like 45 degrees, somewhere in that range. And so that's where that DATS is going to really come in handy, because if it's not present and we've done everything right here, then this cold air mixing through here is going to have less heat for that refrigerant to boil off, in that coil, and that coil is just going to start flooding out. Well, that coil floods out and that superheat starts to drop, then that liquid refrigerant is going to return back to that compressor. It will flush out the oil. That'll cause issues on the compressor. But also here, that saturation temperature is going to fall so low that any moisture that's collected on that coil, the humidity that's in the air, that's going to start to become ice. And it'll start to grow, and before you know it, you'll have a block of ice on your coil. So it's very important to have that DATS right there. I've seen a lot of times where people will take the DATS and they'll stick it down here into the coil. I've even seen them strapped onto the coil. I don't know why somebody would do that, because it's not a coil temperature sensor. It's a discharge air temperature sensor, so it has to be in the supply air plenum. Okay, and you really want it to be as close to the air handler as possible, so it's reading the most accurate temperature, because there is heat gain to a duct system, depending on many variations of how things are ducted out and how attics are ventilated, and some attics are warmer than others. And so if you have this DATS too far away, then it may not be reading the most accurate temperature. The closer it is to the supply air plenum, the less likely it's going to have a misreading. And so it's going to be reading the most accurate temperature. So if there is any heat gain to the duct system, 3, 4, 5 degrees, I might experience a false temperature. If that bypass is right here coming off that supply air plenum, then that's where I want my discharge air temperature sensor to be reading my plenum temperature. And by doing that, I'm going to have more reliability on this coil not freezing up and me losing oil on the compressor. So those low limits are important. Also, the high limit. If I have a warm evaporator coil and I have cool air coming across it, and I'm exchanging, the cooler air onto the coil, and I'm rejecting heat off the coil into the airstream, if this is a heat pump, then the same thing. I'm going to have warm air coming through that bypass the moment one of these supply air dampers close down. And when that happens, my head pressure is going to gain a higher PSI, and I'm going to have a harder time condensing that refrigerant to a liquid. And we don't want that pressure to get too high to where we start having compressor issues there. So again, if I have a high limit setting for my plenum, so I don't reach too high of a temperature there, that DATS will also read that. Same thing, it'll shut that condenser off to help regulate the head pressure on that evaporator coil during heat mode. I'm not going to talk so much about the heat mode, although that when you're in the timeline of watching this video, it could be in any mode. We're just going to refer to this in the cooling mode. It'll be a little bit easier to get through it. So with that bypass opening, it doesn't open all the way. If it does open all the way, when one zone shuts down, then your bypass is not sized correctly. So if I have too small of a bypass, then any one of these zones are going to allow this to open up all the way. So if my smallest zone, I said 1,000 CFM, 650 CFMs, and 350 CFMs. So if my smallest zone is 350 CFMs, then the difference would be 1,650 CFMs worth of bypass that I need. So I'll be basically returning 4 tons of air. So I'm going to need 16 inches of bypass duct in that situation. A lot of times people misunderstand. They think when I size it to my smallest zone, then they think, oh, if my smallest zone is a 10-inch, then my bypass needs to be a 10-inch. Well, if your bypass is a 10-inch in this application, then every time a zone shuts down, no matter what zone shuts down, my bypass is going to open up. And you don't want your bypass to open up 100%. It doesn't need to open up 100%. So if you can see where I've got this, if this is 1,000 and this is 350 and this is 650, then this would be 50% of my air distribution. And so I've got my damper. This would be 100% open. This angle here would represent 50%. So I just kind of said, hey, if this is, and get my color just right here. This as an example, if this is a 14-inch, oops, get my mark down a little bit. There we go. If this is a 14-inch, That's still too big. If this is a 14-inch and this is a 10-inch, and this damper here is a 12-inch. Say this is 650 CFMs. Say this is 350 CFMs. And say that this 14 was 1,000 CFMs. And let's just say my air handler was 2,000 CFMs. Then in this situation, my bypass would have to be 16 inches, right? Because I would need to return, if this is the only one open and these two are closed. Let me go ahead and close these real quick. All right, so we're going to go ahead and close these. And the only one open is my 350 CFM. So now I need to return back 1,000 and I need to return back 650. So in this situation, that damper is going to be open 100%. And how that would look if it was open 100%, it would be pretty much like that. And so that's what I'm suggesting, that I need to be able to take the difference of here and here and move 100% of these two numbers, 1,650 CFMs, back through that. So yeah, you're definitely going to be dumping a lot of cold air right back onto that evaporator coil that's already cold, and we're really going to drop the temperature on that coil to a freezing point. But that discharge air temperature sensor, maybe it's set for 44 degrees Fahrenheit, and the moment that plenum reaches 44 degrees, it's going to knock out that condenser. And that zone over here may be satisfied just moving this volume of air, try to get that 1 degree down, or maintain that 75 over 75, whatever it needs to do, even with the DATs shutting off that condenser. If it hasn't been satisfied yet, then the moment this supplier temperature starts to warm back up, because the coil is now getting warmer, right? What I mean by that is, if I have 75 coming in and I don't have any refrigerant running in through my coil, then I'm not transferring any heat outside. So what's going to happen is 75 is going to come in, 75 is going to come out. That plenum is going to be 75 very quickly, and that 75 degrees is going to be going down to that 350 CFM zone. And with that being said, if that's not enough to satisfy that zone, then that discharge air temperature sensor is not reading 44 degrees anymore. It's probably reading 70, 75 degrees. It will allow that condenser to come back on, which will start the process of evaporating, boiling off that liquid again, because we'll have liquid refrigerant going back into it. And this is always going to happen. So let's just say, for example, the 1,000 CFM zone opens back up. We'll say that the small zone, the 350 CFM zone, say it closes. Okay, so now 650 plus 350, that's 1,000 CFMs. We're moving 1,000 CFMs this way, but we bottled up and we have an extra 1,000 CFMs that can't go anywhere. So what's going to happen is we're going to have less static pressure pushing this bypass open. So what will happen is that bypass will close back down a little bit. It's not going to close a ton, but it'll close about 50% in this situation. And so we'll be bypassing less CFMs of air, right? We're still getting, plenum temperature, supplier plenum temperatures, which can be 55 degrees. We're still getting that 55 degrees that's coming back through on that evaporator coil, which already has a low saturation. So zone systems are safe to use always in the event that everything is sized properly and has the proper protective equipment in there for it to run, so things don't hurt. We don't want to exceed our static pressure on our blower motor, and we don't want to drop down to a very low supply air plenum and risk freezing our coil and liquid refrigerant returning back to that compressor. in the event that we are not, I'm going to try to erase some of this stuff. If in the event that we are not bypassing any air, what would that look like? All right, so for us to not bypass any air, then these zones are going to have to call. They're going to have to open up. All right, we'll go ahead and open this one up over here. And the moment we do that, we lost all the static pressure that's pushing this bypass open because there's no restrictions in the airflow. All right, so what's going to happen is now this damper is going to close, and now this 55-degree air, it's not coming back around to that bypass, and it's not coming back to that evaporator coil. We just have this warm 75 degrees coming in to our evaporator. So I'm going to try to do this again. I'm going to kind of color code some things here. Let's say that this is always going to be blue because it's cold in this mode. Supply air trunk line will be blue. This main distribution box will be blue. And we're going to go ahead and take these dampers. We're going to make them all blue. Why? Because they're open right now. All right. So there we go. Now, I'm not going to label this blue because in this mode, everything is open, right? But we can go ahead and take this return air plenum and we can say, okay, well, that's going to be red. And this return air trunk line, that's going to be red too. So this is pretty much what we're looking at. So we could even go to this evaporator coil and we'll just say that's going to be red. And so, so with no bypass, you're just warm air in, you're exchanging the heat, right? Boiling off that liquid refrigerant in the evaporator coil, returning with an amazing superheat range so the compressor is safe. Everything's good to go. It's nice and quiet, good lubrication, no scroll plates grinding, no pistons making noise, whatever type of compressor you have. The blower wheel is taking in that nice cool air now, and it's distributing it all the way out to all the zones. Now we're going to go ahead and close this one zone down. And the moment we close that one zone down, we're going to go ahead and take this and we're going to just close. Excuse me. We're going to close that damper down there. Okay, so now that damper is closed down. And the moment we did that, we have now 650 CFMs, okay, that's going to create enough static pressure sitting here where it's going to want to open up this bypass. And the moment we open up that bypass, we're going to wind up cracking open just a little bit, not a whole lot, but it's going to open up a little bit. And now we will start to see cold air go into the bypass duct, the bypass trunk line. And with that, we're going to have cold air mixing with this warm air, right? Basically, all of this cool air that's here is now going to be mixing in with this warm air, and you know, that temperature is going to drop even more, and that supply air is going to, you know, run from its, you know, above 50 degree to in those 40s. It's going to naturally drop into those 40s. And that's all this simply is. So if you're afraid to put a bypass duct on there because you think it's going to open up all the time and it's causing problems because every time you've done one, you've been in that situation, you're not sizing your bypass duct properly. And you can't have a bypass duct in there without a bypass damper. And that static pressure is what opens those bypass dampers. And that static pressure is caused from the zone system shutting down a damper. That creates static pressure. And you're putting this here so you don't kill your motor. And then you're putting the discharge air temperature sensor there so you don't kill your compressor or freeze your evaporator coil. And so this is going to protect your compressor and keep your coil from freezing. And this bypass here is going to keep that motor from failing. And that's why those two fundamental things have to be there in every zone system. Doesn't matter if it's a variable speed blower or if it's a standard blower. Standard high torque, ECM, doesn't matter. You know, they're only designed for a certain amount of static pressure, and the moment you create that static, you have to relieve that. And so this bypass is what relieves that static pressure, keeps that motor from failing, but yet causes a second problem, which the discharge air temperature sensor will fix. And this many times we don't see those there, and we don't see those there. Sometimes we see those there and we don't see that there. Sometimes we see both of them there, but it's not sized right. And so it's a very simple process. You just have to not be scared about it, and just you know, watch this video as many times as you need to. Slow it down, rewind it. There's not really a whole lot more to discuss on that. Normally my videos are 50 minutes or an hour long, or some of them 2 hours long. They're very well explained. You know, I wanted to make sure that I didn't release a bunch of 2-hour videos because that takes a lot of time for you guys to find the time to watch that. So we do need some short videos, and this is going to be one of those short videos. So I hope this helps out. Leave me a comment, ask some questions. If you need a little bit more elaborate details, I'll happily do another one for you. But past this, I want to move on from zone systems. I want to get into other subjects. I know everybody's going to be talking about what pressure should be like, what superheat should be like, what should subcool be like. Everybody wants to know what it means. I love that subject, but before I get into that stuff, I want you to better understand that it's hard to explain what those numbers are supposed to be if you don't know how we got to those numbers in the first place. I want to teach you how we get to those numbers, those values on your S-mins, and why pressure in this industry, refrigerant pressures, aren't enough information to diagnose anything. And so you have to understand all these values. So by the time I get into superheat and subcool, there's going to be plenty of heat. There's going to be plenty of years in the industry you're going to have. You're going to better understand it if you watched all these series of videos. Now that we're kind of moved out of the electrical stuff, I've done a lot of videos on just dealing with anything high voltage, low voltage, whether it's heat strips, defrost control boards, relays, motors. We've kind of really spent a lot of time just dealing with power. You know, and then we're started getting into airflow, and the best way to get into airflow coming out of the low voltage side is zone systems, because we're kind of tying the knot there between low voltage, explaining that, and we're tying the knot on you know, one of our biggest issues on zoning. A lot of people are confused on, and that talks about airflow. I did say that I would release a video more on ductwork. I'm not seeing a whole lot of attention on some of these videos when I talk about ductwork, so I'm just going to kind of just wait for you guys to just reach out to me through a comment and say, hey, we'd like to learn a little bit more. If I see that, I'll look for it, and I will release a video talking more about ductwork and Tom's sweet spots. Past that, I need to continue to talk about the mechanical system, and we discuss a lot about losing oil in compressors, and I could talk about this all day long. Just to give you a little quick peek into the next videos that we start to talk about. We're going to talk about compressors, why that's a critical point, and we're going to talk about metering devices, why that's a critical point. And we're going to get into a lot of great detail on that. There's going to be a lot to talk about. There's going to be dozens of videos just on the mechanical system itself. And then we'll never run out of material to talk about, so we're just going to keep on moving on. So like I said, very simple. If you've had problems with this in the past, don't let it be a deal breaker for you. Just circle the wagon, something that's designed wrong on your end, or maybe something that you're working on. Don't be afraid to look at, you know, was something done wrong? You know, if the customer is telling you, hey, I have a new problem, and you go over there and you find this new problem, look at everything, because they may have more problems that they're not aware of. You know, because the moment you fix that, and if somebody ever came behind you from your company or from another company, or you have another issue and that customer is aware that there's other issues that were not addressed, you're not going to look very good, because you're the one pretty much saying that, yep, my signature's on it, you're good to go. You know, it's not very healthy to be in that situation. So be very observative. If you're working on a zone system, you know, find out how many supply air dampers they have. If they don't have bypass, they need to have it. If they don't have bypass and they have no DATs, they got to have both of these for this to work. Once again, as a quick recap, the bypass duct is there to save the blower motor. That's it. So it has to be solved mathematically. It has to be sized to the smallest zone, meaning when that smallest zone is shut down, that bypass has to open up to make up the difference for the remaining zones that are open, right? Um, and so that's always going to be the case. And yes, we're returning cold air. Is that a good thing? No, it's not. It's not a bad thing either, but it's not a good thing if we can't shut down the condenser to stop the liquid migrating back to the compressor, because you don't want to lose oil. You don't want the temperature of the coil to drop to a point to where any humidity that collects on that coil just grows into a sheet of ice, because that's what's going to happen. If that coil is sitting at 30 degrees, guess what? Yeah, you're going to wind up making ice real fast. It'll be a great ice maker, and your customer's not going to be happy that they got an ice maker. So understand that the DATS is there to protect the compressor, and the bypass is there to protect the motor. A lot of people do not understand what they're there for, and so they think because they don't understand it, it's not important. And it's always important to understand what you're dealing with and how you got to do it, and it's very simple. It's not hard. Like I said, leave me a comment. I need those comments. Also, give me a thumbs up. I need those. So help support my algorithm. Share this with somebody else. There's a share button right there. Push this out to your buddy. It doesn't matter if it's a customer that just needs to kind of see what you're learning or what you're talking about to better understand this. Share this with a customer. Nothing wrong with that. It's good for everybody who's either paying the bill or part of why that bill needs to be there to know this information. So everybody needs to be, it's relevant for everybody. Subscribe to our channel if you haven't done so already. As we release videos, you want to make sure that you're being notified as they come out. We do release videos weekly. We took a little bit of a break there. No big deal. It's busy this time of year, but we're back in our groove. So stay tuned. Stay safe. Thank you.